All right, we are going to look at some real geometry proofs today. So we're going to get rid of any of that, silly algebra stuff where we've been solving for like x eventually. So this is what real legit geometry proofs are going to look like, and this is definitely going to be a different feel than those algebra ones that we were kind of looking at, or the ones that were like half geometry, half algebra ones. So I'm going to show you three examples of some easier geometry proofs. And I can just about guarantee you that these three examples may not necessarily instantly make sense to you. And that's absolutely normal. I remember whenever I was first doing geometry proofs as a student myself, there were lots of times where I just looked at the professor like he had 8 heads, and I'm going, how on earth did he just do that? Or I would have never thought of doing that particular step next. Like, where did he just get that from? So I'm just going to tell you, and I'm not going to have any you try problems in this, but I just really want you guys to slowly but surely kind of watch and take some good notes here. And this might be a video that you would definitely want to re-watch or retry the three examples on your own. All right, so first off, what was the name of the angles that were opposite of each other when two lines intersected one another, like angles 1 and 3 or like angles 2 and 4? This was something that we talked about. They were a pair of angles that we talked about last chapter, and they were called vertical, except I don't want to write white on yellow. They were called vertical angles. And what relationship did these angles have with one another? Well, last chapter we really didn't talk about a specific mathematical relationship that vertical angles had with one another. So that's what we're really going to discuss. And you may have some idea of, well, what does it look like may be true about angles 1 and 3? What does it look like may be true about angles 2 and 4? They look like they're maybe the same angle measure. And I would say that that is the case here. That's what we're going to prove is true. So we're going to show that vertical angles are equal or congruent, but we're going to prove why that is true. So the first example, we are going to prove the vertical angles theorem. Now, the vertical angles theorem will be a reason, just like, the addition property of equality, the distributive property, the substitution property, the transitive property. The vertical angles theorem will be a property, a theorem in this case, that you may use in proofs. So if you're ever working on a proof and you're like, hey, there's vertical angles here, and I think I need to use those, well then you could say, that we'll say angle 2 equals angle 4 in a proof, and you can say, I know that's true because of the vertical angles theorem. So this is the one time that we're actually going to prove the vertical angles theorem. So you will not have to reprove it in any other problem, okay? So our given information is basically we have vertical angles. And what we're going to prove is that our vertical angles, and I'm just picking on 1 and 3 in this problem, that those vertical angles are in fact congruent or equal to each other. So basically ignore the 2 and the 4 for right now, but don't cross them out because I'm going to end up using them. All right, so if I want to show that 1 and 4 are really equal here. So again, I need to start off, what's my given information? That angle 1 and angle 3 are vertical. There's my given. And so now I need some help here, right? I need some help. I need to bring together angle 1 and 3, but I can't just instantly say they're equal because of the vertical angles theorem, because that's what I'm trying to prove is the vertical angles theorem. I can't say the vertical angles theorem is true because of the vertical angles theorem. That's called circular reasoning, and that doesn't work mathematically. So this is where I need to call on some help of a different angle. So I'm going to start with angle 1, but I can't instantly get to angle 3. So I'm going to use a relationship that I learned last chapter with angle 2 with angle 1. And what type of angles were 1 and 2? Well, angles 1 and 2 were a linear pair, right? And what's always true about a linear pair of angles? Well, they're always going to be supplementary, but in fact they add up to be 180. Now, we just talked about something not that long ago called the straight angle postulate. And the straight angle postulate works with any number of angles that are on a straight line. And so these linear pair happen to be 2 specific angles, but The straight angle postulate applies to 2 angles, 3 angles, 4 angles, 18 angles that are all on a straight line. So I know by the straight angle postulate that if when I add together angle 1 and angle 2, I'm going to get 180 degrees. And the reason is the straight angle postulate. Now, some of you might go, well, shouldn't we just say that angles 1 and 2 are supplementary? But the straight angle postulate does not state that the angles are going to be supplementary. It states that they add up to equal 180. So I'm being very literal with what the straight angle postulate says. Nowhere in the straight angle postulate does it say that the angles are supplementary. It says they add up to be 180. Now, that's all fun and games if I pair together angle 1 and 2, but that still doesn't let me pair up 1 with 3, which is my ultimate goal here, right? So now we're going to use angle 2, and we're going to see what relationship it has with angle 3. And we find that it has the same relationship that it had with angle 1. So we can go ahead and say that angle 2 plus angle 3 equals 180 degrees, and we get to use the same reason. It's another straight angle postulate. If I can make my angle look like a straight angle there. There we go. Okay, now angle 2 is basically acting as a matchmaker. Okay, we know deep down inside that angles 1 and 3, they belong together, right? They are just soulmates with each other, but they don't know it. They don't know it. So we need a friend like angle 2 to be like, oh man, I see these two angles. They're perfect for each other. I need to help bring them together. And so that's angle 2's goal here, is to bring together angles 1 and 3 and then back out and leave angle 1 with angle 3. So here's going to be our next move in this problem, is we're going to take these two pieces of mathematical equations and we're going to bring them together. Okay? Now some of you might be going, well, hey, I can easily see that, if 1 and 2 add up to be 180 and 2 and 3 add up to be 180, well, I got angle 2 is the same in both equations here and the 180 is the same in both equations. Well, it must mean that I could say that angle 1 equals angle 3. Not so fast there. You're skipping over multiple steps. Now, what is true about both of these equations is they do in fact equal 180 degrees. So what I'm going to do is this. I'm going to start rewriting this equation, and you don't have to draw the arrow down here. I'm just trying to illustrate where I'm getting this information from. But instead of writing angle 1 plus angle 2 equals 180, how about I substitute out that 180 degrees with something else that is equivalent to 180 degrees? Do I have anything else in this problem that I know is the same as 180 degrees? Oh, I do. Angles 2 and 3 added together. So I'm going to substitute out that 180 degrees with what else I know 180 degrees is equivalent to. So this is me using the substitution property of equality, or really this is like using the transitive property of equality. So you get to pick here. You can pick either reason. I like using more substitution, but transitive works as well. Now I've got this new equation that angle 1 plus angle 2 is equal to angle 2 plus angle 3. And remember, angle 2 is that matchmaker, but doggone it, it's time for that matchmaker to disappear and bring together our two soulmates. So how could I get rid of this angle 2 on the left side and at the same time get rid of this angle 2 on the right side? What's that? Subtraction property of equality? I think you're right. So if I subtract away angle 2 from the left side, that leaves me with angle 1. And at the same time, if I subtract away angle 2 from the right side, that leaves me with angle 3. So now, using the subtraction property of equality, notice what I now have. And notice what I'm trying to prove here. So that means we are done. There's our period at the end of our mathematical statement here. There is the vertical angles theorem's proof. We have proven that vertical angles must be equivalent to each other. And how did we do that? Well, we had to use the straight angle postulate a couple times. Bring together those two straight angle postulate equations into a single equation, and then we used the subtraction property of equality to finally prove that that was true. All right, a second example. So Angle QRS and PSR are supplementary. So let's find in our picture where that's at. QRS. So QRS. So really we're talking about this angle right here and angle PSR. So really they're talking about this angle right here. Okay, so let me get rid of that. So really we're saying this angle and this angle are supplementary to each other. And what we want to prove is that angle QRL, which is this angle QRL is congruent to angle PSR, which is one of those supplementary angles. Okay, so how are we going to start off our proof? Well, we're going to start off with what we have been given, that angle QRS and angle PSR are supplementary. And I'll just do SUPP for supplementary. And there's my given information. Now, let's go ahead and take this given information, because it uses a vocabulary word, supplementary. Maybe we should define mathematically what supplementary means here. So what does it mean that these angles are supplementary? Well, it means that angle QRS plus angle PSR equal 180 degrees. And how did I know that? We defined mathematically the word supplementary. Okay? Now, that takes care of all of our given information, which means we now need to go hunt and find something else to use in our picture. Now, we need to somehow talk about angle QRL. But is there a relationship that this angle QRL has with either angle QRS or with angle PSR? And right now, you only know about one relationship, and that's with its adjacent neighbor here, QRS. What do we know is true about angle QRL and angle QRS? Well, they're a linear pair, right? And we have two angles that are on a straight line, so we know that angle QRS added with angle QRL, they have to add up to be 180. And how do we know that's true? That good old straight angle postulate tells us that has to be true. And remember, the straight angle postulate does not state that angles are supplementary. It says any number of angles that are on a straight line add up to be 180 degrees. Now, we're at that same point like we were at the vertical angles theorem, where we've got two pieces of mathematical information here, and now it's time to bring them together. So this all of a sudden is going to start looking pretty familiar. Okay? Because notice in both of these equations we have an equals 180 and equals 180. Well, we had that same scenario happen here back in the vertical angles theorem. And so we get to use that same idea again. So I'm going to take this equation, so angle QRS plus angle PSR equals, but instead of writing that equals 180, is there something else that I know 180 is equivalent to? And again, you're going to be like, well, this really, isn't this like almost the same proof? Kinda. It really is. You're going to see a lot of similarities in proofs like this. And so again, we use the substitution property of equality, or you could call this the transitive property of equality. Either one works out there. You pick one. Don't write both. Pick one. All right. So remember, what was the ultimate goal we were trying to show here? Is that QRL was congruent to or equal to PSR. So let's see. Here's QRL, and here's PSR. All right, cool. So we're almost there. We just need to figure out, how do we get rid of QRS's on both sides of an equation? Man, this is going to be just like that vertical angles theorem, right? If we use the subtraction property of equality, then angle PSR is equal to angle QRL. And so there's the subtraction property of equality. Now, really, to me, I am good with calling that done. Some people would look at this and go, it's not exactly the same thing, right? They're flip-flopped. So if that drives your OCD-ness a little crazy, your obsessive compulsive disorder crazy, and you're like, I don't like that, I don't like that, I don't like that, then you can do one more step if you want, okay? Here's the extra step you could do to flip-flop those. You could say, well, if angle PSR is equal to angle QRL, well then Angle QRL is equal to angle PSR. And what was that property called when we could just flip the sides of the two equations? That was the symmetric property of equality. And then you could call it done at that point. But again, I am good with calling it a day at this point. But if you need to see that flip-flopped, then do the one extra step and use the symmetric property. Completely up to you. All right, so there's the second example. Now let's try this last one. So now notice we have a nice segment here. We don't have any angles going on in this problem. So this one's going to be a little bit different, okay? So we're not going to be using straight angle postulates, vertical angles theorem. We're not going to see any angle stuff going on. So given AB, segment AB is equal to segment DE. Okay, we see that from the problem. Cool. And BC is equal to CD, and it's marked as well in the picture for me. Perfect. What do we need to prove here? We need to prove that AC is the same thing as CE. And some of you are probably scratching your head going, well, yeah, that's true. I mean, look, AC is made up of a 1 segment marking and a 2 segment marking. And look at CE. It's also made up of those two pieces. So yeah, those are equal to each other. And so now we need to mathematically put that together, though. So let's start with our given. So segment AB is equal to segment DE. And then I'll just kind of use the comma notation here. Segment BC is equal to segment CD. That was given to us. Okay. So now, keep in mind, we're trying to talk about segment AC altogether, right? And so it would be kind of helpful if we could talk about some sort of segment postulate that we've referred to in the past. So I know that segment AB plus segment BC is equal to, altogether, big segment AC, right? And that was called the segment addition postulate. And again, I like to abbreviate things like this. Seg add post. That works for me. And remember, we want to talk about segment CE, which is also made up of 2 smaller segments, right? Now, we're going to kind of hold on those temporarily because we want to get to CE, but we're going to get there through a different route. So here's what I want to show you. What could we substitute out segment AB for? What else is AB equivalent to? Well, according to our given, AB is equivalent to DE. So I'm going to make a substitution. But I'm going to go ahead and do 2 substitutions in one step here. And that's okay to do 2 steps in one as long as it uses the same reason. Because what else do I know segment BC is equivalent to? BC is equivalent to CD, right? So I'm going to make a swap. I'm going to make a double swap here. So AB I'm going to swap out with DE. And BC I'm going to swap out with CD. And I'm still going to say that's equal to segment AC. So I just used the substitution property of equality technically twice. Do you have to say twice? No, you don't. I could just leave it as substitution property of equality and call it a day with that line. Okay? Now, DE plus CD. DE plus CD. Oh man, altogether that makes CE, right? But first, we're going to need to do something here. So now I'm going to use that CD plus DE, segment CD plus segment DE, well, that's really the big segment CE. So this is just me going back and saying, hey, segment addition postulate works there too. But now what I'm going to do is take those last 2 pieces of information and help bring them together. Okay? Because what do these 2 equations have in common is that really they're adding together the same 2 small segments, right? Like here's DE, here's CD, there's CD. Just because they're in a different order doesn't mean anything, right? 2 plus 1 is the same as 1 plus 2. So here's what I'm going to do. Instead of writing CD plus DE, what else do I know that CD plus DE is equivalent to according to the previous line? it's equivalent to segment AC. So I'm going to substitute out, based on this equation up here, that this is nothing more than AC. And then I'm going to leave the CE, I'm just going to bring it down from that line. And so again, I use the substitution property of equality. And I have proven what I've been asked to prove up here. So again, I know these are a little bit of a stretch, and I think the more and more examples you see and the more examples you try, it will slowly but surely start to open up and make more sense. I promise that it will. Just stick with me, ask questions, and we will make it through this chapter together.